In this video, we want to explore vectors just a little bit more and talk about how we can use them and some of their properties. All right. Now, vectors live in a coordinate system. All right. They live in a coordinate plane, and we represent them with arrows typically drawn from the origin. So, for example, let's say we have an airplane and it leaves an airport and travels at 250 meters per second due east, and we want to plot this vector. So if I want to plot this vector, we have to do a couple of things. First, we have to define the coordinate system we're going to use. So it's pretty standard to use the typical Cartesian coordinate system, your XY plane, particularly when using directions. And I'm going to put east to the right and north upward. And really those are the only two directions you have to specify. You only have to specify two directions, because then it would be implied that this would be west and this would be south. Now, for this particular problem, we want to plot an arrow that starts at the origin. This would be our point of origin. And we want to make an arrow that represents 250 meters per second. Now, when you're drawing arrows, when you have a problem like this, it really doesn't matter how long your arrow is, right? I can draw an arrow that looks like this, and I can call that 250 meters per second. So that arrow represents the velocity of the plane in the direction east. Okay, but when you have multiple lengths in a problem, multiple vectors, you want to draw your vectors so that they are at least as close to scale as possible. Okay, and we'll see how to do that here in just a moment. But one fundamental thing to note, okay, before we leave this example, I don't have to draw my vector from the origin. All I'm doing is traveling east. So I can actually move this vector around at will if I wanted to. I can displace it up here. I could even move my vector over here. And all three of those vectors represent the exact same thing. I just have an arrow pointing in the eastward direction. So a vector is an object that lives in a coordinate system, and I can move my vectors around. I can displace them in the coordinate system as long as I don't affect their length or the direction. So any vector that represents 250 meters per second in this coordinate system, any vector that represents 250 meters per second in the eastward direction is a valid vector. Okay, so I can move my vectors around at will. Now, one fundamental problem that we will see is looking at changes of velocity when the direction changes. So far, we've only looked about moving along a straight line. Okay, so now, for example, let's say we have an initial velocity of 4 meters per second east. So you're traveling in the eastward direction, and then you turn and go north, and then you're traveling at 3 meters per second. Okay, and technically we need our arrows here. So I want to find what the change in my velocity is if I have these two vectors. So I'm going east and then I'm going north, and I want to find what the change in the velocity between these two vectors is. So first of all, let's plot our situation. We're going to define a coordinate system, and initially we're traveling at 4 meters per second along the eastward direction, And note that I'm now saying that this vector represents 4 meters per second, so my 3 meters per second due north should have a length of about this, right? So it should be a little bit shorter, because I want to draw this to scale as closely as possible. Okay. Now, here's the question. What is the change in the velocity? Now, remember that vectors have both direction and magnitude. When we ask this question, what is the change in the velocity, for the lower courses, all we have to worry about is the magnitude. So I'm going to put an absolute value sign over this, and that just says I just want to worry about the magnitude of the velocity, or the change in the velocity. Okay. So now how do we answer this question? Well, one might be tempted to say, well, what about this? Right? Couldn't that be delta V? And the answer is not quite, but close, okay? And here's why. If you think about traveling east and then traveling north, you're not changing in this direction, but you're changing in that direction. And so what we do is use the property that we just explored about vectors, that I can move my vectors around in my coordinate system. So here's what I'm going to do. The way to find the change in velocities when you're doing this type of problem is to originally our 3 meter per second vector was here, and I'm going to move it so that it's now at the origin. Okay? I'm going to move it so it's now at the origin. And it's going to look something like this. Okay? And now, here's the trick. Draw another vector from the tip of your first vector toward the tip of your second vector. And one thing I haven't mentioned yet, when we're representing vectors with arrows, the point of origin of the vector is called the tail, and the point at the other end is called the tip, right? So the tail and the tip, or the tail and the tip in this case. So delta V we draw a new vector from the tip of VI to the tip of VF. Right? Okay, and this new vector, once I displace VF to the origin, and I draw a new vector, then the resulting new vector that I get is going to be delta V. All right? And if all I have to worry about is the magnitude of delta V, all I want to do is calculate the length of delta V. And what is the length of delta V? Well, the length of delta V is going to be, we can see that we have a right triangle here. So as long as my direction changes are perpendicular, okay, to each other, then I'm going to always have a right triangle here, and I can calculate delta V by calculating the hypotenuse here using the Pythagorean theorem. So what is delta V? So delta V, the magnitude of delta V, okay, is going to be equal to the magnitude of VI squared plus the magnitude of VF squared, right? And I'm drawing magnitude signs here because at this point I don't really care about their directions. I don't care that this is east and I don't care this is north. All I now care about is that this is 4 meters per second and this is 3. I'm taking the directions into account by noting that this is a right triangle, okay? So just to get the length of that vector, now all I do is plug in my values, and VI is 4, squared and 3 squared, and our units are going to be in meters per second. And this is going to give me the square root of 25, and I'm going to get 5. Now, a couple of things to note. Remember, whenever you take a square root, you should technically have a plus or minus here out front. I'm dropping the plus or minus because magnitudes can only be positive. It doesn't make sense to say that I have a negative length. I can have objects moving in the negative directions, so I can have negative displacements, but I cannot have negative lengths of vectors, okay? So the length of this vector is going to be 5 meters per second. So this vector represents 5 meters per second. So the change in my velocity was a change of 5 meters per second. And for the upper courses, when we start to talk about direction, the direction is going to be this angle right here. We're going to typically measure angles with respect to the x-axis. Or, actually more formally, it would really be this angle right here. Okay, that is the angle that we're going to talk about when we talk about the direction of the change in motion for the upper courses. For 151, you don't have to worry about that. Okay, all we're going to worry about is what is the magnitude of this change in the velocity. Okay, so you're going to see this particularly in chapter 4 for the 151 courses. And then in chapters 3 and 4 for the upper courses. So I did want to mention that, and I hope you found that helpful, because I know that that can be a little bit confusing the first time you see it without any examples. So I hope that helps. All right, we'll see you next time.